Hi, and welcome to the Institute of Aquarium Australia's Respirable Crystalline Silica webinar. Hi, I'm Paul Gerber. I'm a Principal Hygienist at Ohms Hygiene. I've been doing hygiene for about 20 odd years now, but also worked in the health and safety area across mining, quarrying, industrial sites at both a corporate as well as a on-site basis. So today I'm going to take you through a couple of different aspects of respirable crystalline silica and how to manage those particular issues. So in today's webinar for respirable crystalline silica or RCS, we'll look at the introduction to RCS, but also the workplace exposure standards and how they've changed and implications in those areas. So with the introduction to RCS, we'll look at what activities actually generate the dust, dust and particles size and implications on health, the exposure results, but we'll also look at the types of silica and where they come from, but also the hazards of RCS on the human body. We'll also look at the workplace exposure standards. What are the current exposure standards? Because there has been a change across some of the states going forward. Also the workplace exposure standard adjustment for extended shifts. So if it's greater than 40-hour week, there is adjustment requirement, and we'll actually go through that and how it works. But we'll also have a look at some of the examples of extended shifts, so it gives you an idea of how it lowers it going forward when you've got extended shifts greater than 40 hours per week. The first topic we'll cover is the introduction to respirable crystalline silica. Dust is generated during quarrying activities such as extraction, drill and blast, crushing, screening, hauling and stockpiling aggregates, construction materials and sands. This isn't the only activities that generate dust. You've also got dust that will be blown in from adjacent properties. If you're in a rural area, can be from farming activities that actually blow dust across your activities as well. Maintenance activities can be generate a significant amount of dust, and it's sometimes overlooked. Things like blowing down with compressed air, especially clothing, which generates dust again. Electricians blowing out electrical cabinets to reduce the dust levels before they work on it. Sweeping up with a broom in workshops and having dust become airborne again. Not clearing down equipment prior to maintenance. And also, if equipment hasn't been washed down, pieces of mud and stuff dropping down off the equipment and hitting the ground and regenerating some of that dust as well. Unless there's a robust controls in place, dust will always be generated, causing health issues. Quarrying, no matter what the mineral or materials that you're trying to recover, it is a dusty process. In this section we're talking about dust, and it's not specific to respirable crystalline silica, but dust in general. So some dust will cause minimal health effects, but still cause irritation or aggravation pre-existing respiratory problems. Not all dust will cause long-term irreversible health effects. These are sometimes referred to as nuisance dusts. Other dusts can be toxic, like in this section we'll cover respirable crystalline silica, but also lead and some of the heavy metals will also cause significant health effects. Some of these particles aren't respirable size, they're actually large particles, but they actually have a health effect where they actually absorb into your bloodstream. So size of the particle within respirable crystalline silica, so size does matter. There are two main classes of dust particles, they're inhalable and respirable. We'll cover these in more detail over the next couple of slides, but there's two other additional classes of dust. These are called extrathoracic and thoracic dusts. The extrathoracic are large particles that are trapped in your upper airways and are part of the inhalable fraction, but sometimes they're referred to in literature. The thoracic fraction, which is quite a small particle, penetrates beyond your larynx. The thoracic fraction is seldomly determined, as there are a few exposure standards based on this fraction. So the two main ones that Australian standards or workplace exposure standards are inhalable and respirable fractions. So we'll look at inhalable dust in a little bit more detail in this section. They're also referred to as total dust. So the differentiation between inhalable and respirable dust. Inhalable dusts are greater than 100 micron and predominantly filtered out through your nose and conductive airways, your bronchi and bronchial If you have a look, the human hair is roughly 50 to 70 micron in diameter. We're talking about particles that are actually larger, predominantly larger than the human hair. Large particles are usually coughed up, spat out, or swallowed, and don't normally cause a lot of health issues unless they contain heavy metals. But then we look at that component separately. We look at the inhalable, but we also monitor and measure for those particular heavy metals that may have been of some concern. Inhalable dust is a total amount of dust that can be inhaled and contains both the respirable and non-respirable fractions. So if you look at the diagram on the right hand side, like I said, the human hair's 50 to 70 micron in diameter. Fine beach sand's around 90 micron in diameter. So we're looking at the fine beach sand and above type of material. The mines departments across Australia are starting to become interested in inhalable dust due to the potential to cause other health issues due to the toxicity of some of those components I talked about earlier. And like I said, the inhalable dusts that we're looking at are visible and they're predominantly larger than a human hair. So respirable dust is what we're really interested in today, as a respirable crystalline silica is a subset of the respirable dust. So when we monitor for crystalline silica, we're actually taking a respirable dust sample and we're looking at crystalline silica within that sample. So the respirable fraction is less than 10 micron. These particles can penetrate deep into your lungs within the gas exchange area with the alveoli, which is pretty much the end part of your lungs, which exchanges with your bloodstream. The particles that can enter deep into your lungs are called respirable dusts. Like I said, crystalline silica is just a subset of your respirable dusts. These particles are normally too fine to see unless under specific light conditions. So just because you don't see them doesn't mean that you don't have respirable dusts within your area. And if we have a look at the diagram again, human hair is 50 to 70 micron. We're really looking at the bottom part, what they also call within the environment areas PM10s, so particle matter 10 micron or below. So we're looking at, in that area, we're looking at dusts that are dust, pollens, molds. That's the sort of size particle that we're looking at. Like I said, just because you can't see the dust doesn't mean it's not there. You need to monitor your dust levels, and particularly for respirable dust, to actually determine if you have any there. On this slide, we're just looking at the size of various air contaminants that we're exposed to on a regular basis. Again, 1 millimeter equals 1,000 microns. So 1,000 microns is quite a large particle, and will basically drop out of it fairly quickly. Where your smaller components will actually, like the respirable, will actually be airborne for quite a number of hours before it actually settles out, and that depends on atmospheric conditions as well. So if we look at your total inhalable range, we're talking about from 0.01 up to about 100 micron in size. And again, your respirable fraction that we're interested in today is really from 10 micron downwards. If we look at are they visible or not visible, roughly from 100 micron upwards is visible to the human eye. below that, it's only visible by microscope. And once you get down to less than 1 micron, you really need an electron microscope to actually see those particles. So the respirable dust you cannot see under normal light. So this just gives you an idea of where our dust sort of sits compared to other contaminants that you may be exposed to through your normal life. Here we're talking about crystalline silica. Just be mindful not to use the term respirable crystalline silica instead of crystalline silica. Crystalline silica is one of the most abundant natural minerals that make up the majority of components of most rocks and soils. When we're talking about respirable crystalline silica, we're talking about the size fraction that's less than 10 micron that you potentially can breathe in. So make sure that you differentiate between crystalline silica and respirable crystalline silica. Silica occurs in crystalline and non-crystalline forms. And it's important to understand what crystalline silica content that your material that you're mining or quarrying is, and that will give you an idea of what type of risk that you have. As a rough guide, granite's got 20 to 40%, shale's got about 22, natural sandstone's about 67. But you've heard or noticed in the news about composite engineering stone. It's greater than 90% and it's bound in a resin. So when you cut it or grind it, it releases a significant amount of respirable crystalline silica. Crystalline silica also can be referred to as quartz in some of the literature as well. As you might be aware, there's a significant amount of high-profile cases within the engineering stone. This is mainly due to like I said, the very high levels of crystalline silica, where they've been exposed to high levels of exposure over a short period of time, and a significant amount of small workshops don't have or have limited controls to actually capture that dust. So this is why it's important that you know what you're working with, know what your silica content is, so you can actually do a proper risk assessment to determine what best controls are to be put in place to minimize your exposure. Like I said in the last slide, the sites really need to understand the materials that they're acquiring and processing, not just the crystalline silica components, but other chemicals that may be present in your dust, because some of the heavy metals have got very low workplace exposure limits, which means you might be monitoring your dust levels and they look okay, but you might be actually triggering some of those exposure standards for your heavy metals. So you really need to know what you're quarrying, and by doing a geochemical assay of your materials that you're quarrying or processing, that will give you an understanding of what chemicals that may be having adverse effects on human health. You also, like I said, you should understand what percentage of crystalline silica that you're handling. If the concentration is greater or equal to 0.1, it's actually classed as a hazardous substance due to it being also classed as a carcinogen. The International Agency of Research on Cancer has actually classified crystalline silica as a Category 1A carcinogen. This also triggers that, because it's great, if you've got a concentration greater than 0.1, you also require by Australian legislation to actually have a safety data sheet for that product if it's being sold to the public, but also if you're using it internally. So it gives people an understanding what they're being exposed to and what controls should be put in place. You also should know the hazardous substances that may be present, example of heavy metals like I just explained earlier. Now we're talking about respirable crystalline silica. These are particle size, like I said, are less than 10 microns, so we're talking about the small fractions. So respirable crystalline silica is an aggressive lung damaging dust, able to penetrate deep into your lungs in significant quantities. these are the dusts that can actually penetrate down into your alveoli, and that's the section where the oxygen and the bloodstream interact. So if you've got significant particles, they actually cause a lot of damage, and your lung function actually decreases significantly. As you can see on the right hand side, that's actually a picture of a male facial hair under scanning electron microscope. The facial hair is quite large in this picture, and if you have a look at the respirable crystalline silica dust particles, they're very, very small. Like I said, they're less than 10 microns. Some of these are probably down to 0.1 of a micron. They're very small. As you can see, they're significantly smaller than human facial hair. This also highlights why it's important that if you are wearing a respirator, that you must be clean shaven. So if you're not clean shaven, these facial hairs potentially can act like tent poles and hold the mask up, which you won't be able to see, but it'll hold it up significantly enough to allow those small respirable crystalline silica particles to actually travel between the facial hairs and get into your breathing zone and into your lungs. So this is why it's so important that if you are wearing a respirator, that you're fit tested, and two, that every time you wear a dust mask that you actually have a clean shaven face. Otherwise, there's potential for these small particles to bypass the mask and go straight into your lungs. The other type of silica that may be present is amorphous silica. Amorphous silica is also hazardous to your health, but has not been classified as a carcinogen. Most of the effects are reversible when exposure stops. Progressive fibrosis has not been observed in amorphous silica as it has in exposure to respirable crystalline silica. Animal studies on synthetic amorphous silica indicates inhalation exposure is associated with inflammation of the lungs, cellular infiltrates, reversible fibrosis, but also has reduced lung function following acute, intermediate and chronic exposure. However, in contrast to, like I said, to crystalline silica, progressive fibrosis was not observed and most effects were reversible to some extent. Like any dust, exposure should be kept to a minimum. Dust, if you've got a pre-existing health condition, lung function concerns, any dust will irritate that or aggravate pre-existing conditions. So the best way to control it is minimise exposure wherever you can. So I just want to reiterate on the respirable crystalline silica, or RCS. Crystalline silica has been classified as a category 1A carcinogen by the International Agency for Research on Cancer, or the IARC. Respirable crystalline silica dust is created when crystalline silica is broken down to less than 10 micron particle size and released into the air. This can be via drill and blast activities, excavation, so just breaking up your rock at the face, grading material via screening, loading in the back of the trucks, transporting around your site and generating dust from the wheels of the trucks, your crushing circuit to basically get it down to a particular size, and basically any activities where you've got machinery interacting with that material and potentially breaking it up has the potential to release respirable crystalline silica. So breathing in respirable crystalline silica can damage your lungs and can lead to serious heart diseases such as silicosis and lung cancer. And this will be further explored during the face-to-face presentations and going into a lot more detail on the various types of silicosis and the other diseases associated with respirable crystalline silica. So in this section, we'll be looking at the workplace exposure standards. What is the current exposure standard for respirable crystalline silica? Workplace exposure standards adjustment for extended shifts. And also we'll look at some examples of shift adjustment and where to find that information on how to do the adjustments as well. So we'll look at the workplace exposure standard, or WES. Safe Work Australia have published the workplace exposure standards for airborne contaminants. The latest version was published on the 16th of December 2019. Be mindful that not all chemicals actually have an exposure standard. Where this occurs, you can use international standards as well, but be mindful that they are researched and there's enough information to use those exposure standards. So the new exposure standard for respirable crystalline silica has been issued back in December at 0.05 milligrams per cubic meters. So the previous WES for respirable crystalline silica was 0.1 milligram per cubic meter. So they've basically halved the exposure standard. This is applicable to an 8-hour, 5-day week, so a 40-hour week. This standard can only be used for a 40-hour week. If you were to do 12-hour days, 5 days a week, and you've got 60 hours exposure, you must do an adjustment, and we'll cover that over the next couple of slides. So all the states and territories have accepted the new Safe Work Australia workplace exposure standard. However, due to the legislative framework, only a few states have adopted the new exposure standard for respirable crystalline silica. Many will need to amend their acts and regs as they contain the exposure standard within those regulations. So they'll need to change those before they make it mandatory for mining and quarrying to actually change those. So if you look at the table, Tasmania hasn't set a date as such. Victoria adopted it the day after the new standard came out. New South Wales won't change theirs over till the 30th of September 2022. Queensland, Northern Territory, no date has been set. Western Australia is the same. South Australia looking on the 1st of July 2020, and the ACT, there's no date set to actually change their WES as well. But saying that, it will come into effect. It's probably worthwhile to start looking at your current exposures and set the limit, even if it's at an action level at this stage at 0.05, where the states haven't regulated it yet. Just to start looking at your data and putting controls in place to reduce your exposure down to below the 0.05 now, because eventually it will come in within the next 5 years. So the workplace exposure standards set by Safe Work Australia are all based on an 8-hour, 5-day working week. Where the shifts are longer, the time-weighted average exposure standard needs to be adjusted to compensate for the greater exposure during the longer shifts, but also the decreased recovery time between shifts. So you need to adjust it to lower the overall exposure, so you don't put people at risk of exposure to not just respirable crystalline silica, but any other chemical or contaminant that may be present on your sites. We'll look at the workplace exposure standard adjustment. There's no regulated method to adjust workplace exposure standards, but there's a guidance on several methods via the Safe Work Australia document, Guidance Interpretation Workplace Exposure Standard Airborne Contaminants, which was issued back in April 2013. The only exemption is Western Australia and Queensland, who provide guidance and to use the Quebec model. The Australian Institute of Occupational Hygienists, or the AIH, preferred method is the Quebec model. A copy of this Microsoft Excel tool is available via their website. It's a very worthwhile tool to adjust your workplace exposure standards. It's fairly self-explanatory. So yeah, definitely a worthwhile tool if you're going to be doing those exposures. If not, just make sure whoever's doing your monitoring, if it's an occupational hygienist, that they actually do those adjustments, and they're provided with what your rosters are to make sure that they're correctly adjusting for those standards as well. There's several other adjustment models that you can use. There's a brief and scalar model, the US Occupational Safety, Health and Administration model. There's a pharmaceutical model as well. Look, all models provide valid methods for adjusting the standards. The main difference is they do look at the degree of conservatism. Some are more conservative than others. Others have been adapted, and the Quebec model looks at the toxicity of the chemical as well, where some of them don't look at that and do a very basic calculation. All valid, but the Quebec model would be probably one of the preferred ones, especially it's been endorsed by the Australian Institute of Occupational Hygienists as well. We'll have a look at a couple workplace exposure standard adjustments. We'll assume that we're going to use the 0.1 milligram per cubic meter exposure standard, which is based on a 5-day, 8-hour roster. So if we look at the first one, we're looking at a 5-day on, 2-day off, 10-hour day. We need to adjust this. So the things we need to know is, number of days in a week cycle is 7. Number of hours worked per cycle is 50. And the average number of hours per week is 50. So when we can use the Quebec model, and so your adjustment factor there would be 0.8. So your new exposure standard is 0.08. It just brings it down so none of your employees, contractors, workers should be above 0.08 maximum. Ideally, you want to be down to 50% of that as an action level of 0.04. But yeah, you want to be below 0.08. So if you're working a longer shift, so you're doing 14 days on, 7 days off, and 12-hour shifts, you'll see that your adjustment factor drops down to 0.71. So your new shift adjusted exposure standard is 0.07. And again, that's dropped by 0.03. So you really want all your workers below that as well. If you've got an even time roster, say 7 on, 7 off, but you're working a 12.5-hour day, your adjustment factor is now 0.91, or your exposure, new exposure limit is 0.09. It actually goes up because you've got a longer recovery time between your exposures, and you're doing basically less days on than you would be on a 14/7. The interesting one is if you do a shorter week, say you work only 4 days on and have 3 days off, and you're only working 7.2 hours, you still will come up to 0.1 milligrams per cubic meter as your shift adjusted exposure. Even if you do less than 40 hours, it's still going to be 0.1. It doesn't go up higher. It will be 0.1 if it's shorter than a 40-hour week. And look, you're required to make these adjustments, and like I said on the earlier slide, make sure when you do get any of your reports from any of your consultants or even your own hygienist that they've actually got the shift adjustment highlighted on the report. and make sure that the rosters are correct, because if you get the rosters wrong, as you can see in this one, your actually shift adjustment will be wrong as well. So be mindful, have a look at your monitoring programs, have a look at your reports to make sure that this data is correct, because if you don't get this right, you're potentially spending a lot of money on controls that may not be necessary as well. The Institute of Quarrying Australia has invested in the development of a face-to-face workshop on respirable crystalline silica, which will be scheduled for delivery once COVID-19 restrictions are lifted. The workshop will cover information from this presentation in further detail, as well as the health effects of respirable crystalline silica, health risk assessment, control mechanisms, measurement and monitoring of exposure, communication and training requirements, as well as development of a principal hazard management plan, in particular for respirable crystalline silica. Thanks for listening. Any further details, please contact education@quarrying.com.au to register your interest in the up and coming workshops once they're available. Thank you. A range of fact sheets have also been developed on respirable crystalline silica, which are freely available from the Institute of Quarrying Australia's website at www.quarrying.com.au. So please have a look at those. It contains a lot of useful information on respirable crystalline silica.